So I am super excited to have Yael Vinker come visit us today. Yael is a postdoc at MIT with Antonio Torralba, and before that she received her PhD from Tel Aviv. From Tel Aviv. Yael is a recipient of multiple Best Paper awards at SIGGRAPH, and I like to say that she is one of those special unicorns that was formally trained both in graphic design, it's not really it's communication design, visual communication, yes, and computer science. And she really brings these two things together. Very excited. Thank you so much.
Okay, hi everyone. So I need to choose because I want to stand next to the screen. So I guess I will stand here. If you want, I don't know, if it puzzles you, you can move here, but you don't have to. But I can only be at one place. So thank you, Shiri, and thank you all for coming. I'm Yael, and today we'll talk about my research on bridging generative models and visual communication. So probably you've heard the term generative models, especially recently. But visual communication might be a new term to some of you, and today I will tell you all about it. So I have an intro slide, but Shiri introduced me so well, so I can skip it. But indeed, the most important part here is that my passion to this field and the way I formulate the problems that I want to solve come from this early interest of mine in the combination of visual communication and computer science. Okay, so my research spans computer graphics, computer vision, and machine learning, which is also called AI today. And this will be our map for today. So this map summarizes my research over the years across 4 different lines of work. We'll talk about algorithms for abstractions, algorithms for sketch generation, for parametric generation, and visual exploration. But before we can talk about any of these, we need to start with explaining what visual communication actually means. And for that, let's play a small game. You can participate, but it will be quick. So can you think, how would you draw this object if you have the constraint of using as few lines as possible? So you can suggest what would be your strategy? Wheels? Okay, why? Because
it has wheels.
Okay, because you know how this, yeah, but you know what wheels are, and you know what this object are, and you know how it functions, right? But these are not regular bicycles, it's also like electric bikes, so maybe the battery is also important. So you start to analyze what this object is, and make some important decisions on how to depict it under the constraint of using as few lines as possible. Now, maybe most of us will end up doing something like that, okay? But now I want to make it more challenging. Now, if you have to remove something, what would you choose?
Pedals.
Pedals, okay. Everyone said the pedals. It's very interesting. Are the pedals less important than the seat or the battery? I'm not sure, because without pedals we cannot use the bicycles. But it's pretty interesting and it's challenging. But what if you have to remove more and more and more at some point, you probably cannot remove anymore. So this is pretty challenging. And now I want to ask you another question. How would you implement a computer program that can do something like that? Think about it and keep this thought in mind. And this is one example of visual communication. So we use visual means to communicate something under a set of constraints. And actually, visual communication is all around us. So all of you, all the time, even now, consume visual communication. So it exists in traffic signs, in commercials, in maps, even when you use emojis. All of these are human-made visual artifacts that help us to exchange information more efficiently. And they were designed under some constraints. And also, visual communication is very important in academia. So all of us, we sketch all the time. We have whiteboards everywhere. Because sometimes words are not enough. So we draw when we teach or when we brainstorm. We have to design figures that help us to communicate the scientific findings. And across the discipline, scientists invent these visual conventions that help us to formulate ideas and to communicate. So visual communication is very important. It's core to our cognition, our interaction, and our intellectual work. And this motivates my research, where I want to develop computational systems that can engage in this full spectrum of visual communication. So this range from models that could actually communicate through free-form drawings and help us to brainstorm or participate in more creative processes, to models that can produce more polished designs that are also editable, that can help us to communicate very complex information, for example, in science or education. And all of these pose distinct challenges.
Sorry.
Yes?
So just to clarify, when you talk about engaging communication, you're talking about the one end, it's always producing visual artifacts for human consumption, correct?
Yes, so engaging is indeed a wide term. So it means participating meaningfully. So it's not only, so of course it includes also generating, but the key is that it needs to be generated meaningfully so that it could be useful in some way, okay? And we'll see that this goes maybe beyond just generating beautiful images. Okay, so okay. So today we know that we have models, generative models, that can generate amazing images. With the simply by typing text, we can generate these high quality images that are very photorealistic. This is quite amazing. But maybe you notice that our images are quite different, the visuals that we use in visual communication. And they look different, we'll dive into that. And they also pose distinct challenges to existing models. They are abstract, and we saw that it's not trivial to abstract. They should not only be beautiful, they should often function properly. We'll also talk about that. And they might be sometimes a part of a process. So it's not just one-shot generation, we also use them as part of a thinking process. So we'll start with abstraction, which is also where I started my research journey. So a question that very interests me is how to abstract automatically. And we saw that it's not pretty trivial. We saw with the bicycle example. We can abstract in many ways. Different people abstract in many ways, and there are also multiple solutions. It's not just one ground truth. And also, very abstract images are at a long tail of distribution compared to all images we have online. So this poses distinct challenges. And in the first work we'll talk about, Clipasso, we explore visual abstraction through the lens of sketch depiction, which is a very natural lens to explore abstraction because we all use sketches all the time. So in Clipasso, our goal is given an input image of an object. It's similar to the exercise we did. We want to generate sketches with different levels of abstraction that depict the essence of this object, okay, such that it can be recognizable. And our key insight is that abstraction is not only what we see, it's also what we know. So for example, some of you chose the wheels, right? Because we know how bicycles function. So to abstract properly under a certain task, we need to also understand what this object is. And by the way, the name Clipasso of the paper is inspired by this famous artist by Pablo Picasso of the abstraction of the bulls. Okay, so how do we do that? Prior to Clipasso, we can generally divide sketch generation into two classes. The classical approaches aim to find meaningful edges in an image only based on changes in pixel intensity. So all of these works has no what we call notion of semantics. So these filters cannot really understand that what they are depicting is actually a horse. On the other hand, later on, data-driven approaches started to emerge, where the goal is to learn how to draw by finding meaningful patterns and statistics in some human-drawn sketch data. But this approach has some inherent limitation. Because existing sketch data sets naturally were drawn by humans, and they also they are pretty small in scale, and they don't span the diverse classes. So all of the existing works before Clipasso could only generate sketches of specific classes like a cat, a dog, a horse, and so on. And also these data sets don't have different levels of abstraction. So in Clipasso, we overcome this by proposing a new approach, a new way to think about this task that is inspired, by the way, by how humans draw. Okay, so we have three key components to our approach. The first one is the representation, where we use parametric representation. Instead of representing a sketch on a pixel grid, we represent a sketch with a set of curves. So these are called cubic Bezier curves. They are widely used, by the way, to represent sketches computationally because we can see their nice and smooth appearance. We can think about them as a linear, recursive linear interpolation between the control points of the curve. And we can basically render them in any resolution. So this is why we also like vector graphics in general. So while this was used previously for sketches, we use this explicit parametric representation to control the level of abstraction. So we'll be able to create sketches that are more abstract by constraining our domain. So we're using less and less strokes. Secondly is that we don't train any network here. Our learn parameters are the control points of these strokes. And we want to learn how to move them around the canvas to depict our desired concept. And this is inspired also by how humans draw, where we have this limited tool, a pencil, and we need to figure out how to solve the task with our limited tool. So here, the only thing we can do is to move around the stroke parameters. Now, how do we learn these displacements? So our idea, instead of using directly a human-drawn sketch dataset, we'll use a pixel-based prior. Okay, so we can render our parametric representation into the pixel space. This mapping is called rendering or rasterizing. And today we have very nice differentiable renderers, which means that we can also backpropagate gradients through this entire process. And then, questions so far? Okay. So then what we want is that we'll have some pixel prior that could tell us if our rasterized sketch is similar to our pixel image. Now, what will be our prior? So in Clipasso, we propose to use CLIP, which is a vision language model, instead of, again, directly training on sketch data. So in a nutshell, what CLIP is, CLIP is a paper that came out around 2021, 2022. It's from OpenAI. And CLIP was the first open source large-scale model that was trained on both images and text together. And until today, we explore the representations that were learned by this objective. So basically, they proposed two encoders, these are neural networks, that were trained with the objective of mapping images and text to a shared latent space, which is a very interesting objective, such that corresponding embeddings of corresponding pairs lie closer to each other and vice versa. In the same way that if we see a photo of a cat and we hear the word cat, we know that they may resemble the same thing. So CLIP has learned very interesting representation. One of the things that I like the most is that in the paper they show that CLIP can encode images with very different appearances and encode their semantic meaning. So we as humans have this remarkable ability to look at these images that their pixel statistics are very, very different, but we understand that all of them depict a banana, despite they look so different. And it's highly non-trivial that models can do something like that. And especially back at the time, it's not so long ago, it was remarkable. And for us, for the task of sketching, it's very important because sketching is about finding some shared representation between two images that look very, very different. So we leverage this new capability, and we use CLIP image encoder in the following way. So our first loss term, which we name as semantic, is defined as the cosine distance between the CLIP embedding of the rasterized sketch and the input image. So this is a common way to use CLIP because of the training objective of CLIP. But can you think what happens if we use only this loss to optimize our parametric representation? Any thoughts? What can happen?
I would expect it to work.
Okay.
You'll get the horse back.
What?
You'll get back the horse.
Yeah,
Yeah, but in what way?
you accidentally press next.
Oh.
I think
Was it a while ago or no?
No.
Oh.
I think what will happen is we'll get the correct class, but not the right instance.
This is exactly what happened. Okay. So thank you, and sorry for revealing the truth. But basically, what we saw is that we get this sketch that depicts some horse-like features. So we have the tail or the legs. It feels horsey, but it's not our horse. So we lost the identity of our horse, which we define as the geometric feature. Yes.
So this, in some sense, just shows that there's a shortcoming, or some shortcoming of CLIP.
Yes.
And
Well, a shortcoming depending on your goal, because maybe it could be like good in some settings. But in our case, we lost the fine. Clip is known for not being so good in fine-grained visual.
That's because of the way it was trained.
Right, exactly. It was just trained to exactly because until we get to the final representation, the objective was to pick pairs of images and text. So here in this embedding space, a lot of the more fine-grained details of the image might have been lost already.
Because of the nature of the text and different details. The
Yeah,
text is
probably.
unlikely to refer to details.
Yeah, probably.
I think if you asked a person to describe the image without telling them what it was, why they were describing the
I would
image,
just say a horse.
and then have another person draw the image from that description, you get the same phenomenon.
Exactly, right. And this is something that I find to be very interesting because what are the features that we get from seeing an image that maybe we cannot get from only describing it with text that we do today extensively. Okay, so to overcome this limitation in our work, we propose to use another loss term, which we name L-geometric, defined as the L2 distance between intermediate clip activations. And we find that specific early layers in clip encode a very good balance between geometry and semantics. And by the way, if you see the paper later, we explore each layer, and it's very interesting because each layer learns something different. And we find manually what were the layers that produce very plausible results for our case. So our final objective is to find a set of stroke parameters that minimize the sum of L-geometric and L-semantic. And this is an iterative optimization process. Now let's look how the strokes converge. It's very nice. So we start with a randomly initialized set of strokes, and then iteratively we feed the rasterized sketch and the image, and Clip guides the strokes where to go until we converge to these solutions. And you can see that here we have 4 different levels of abstractions that were made by a strong constraint of predefining the number of strokes we use in the optimization. Yes?
Just understand, so there's no training here. I mean, you just took clip. Like,
Yes, we don't
the
do
only training
anything,
is
it's
clip,
just
but you just take
inference
clip.
time
Yeah,
optimization.
yeah.
So there is training of the parameters
Yeah,
of the
clip
control
is trained,
points,
right,
but we don't train any model, we only distill the prior of the clip. Yes.
So what do you think of as the purpose of the sketch? Like, why do you think that you seem to have decided that geometry is important, for example, but some other things like the texture is not important?
Mm-hmm.
Why?
Okay, so of course, always deciding what's important is depending on your goal. So here in this work, we explore visual abstraction through the lens of sketches. So we already decided that the representation we will use is sketches, and there are plenty of reasons to use sketches.
No, but you can use some of the lines in the sketch to indicate texture. Like you have 2 different cats, and one is spotted and one not. Maybe you do spots, maybe not.
Right. So it's not that we eliminate texture completely. For example, if you have a cow and it has the dots, we might draw.
the giraffe.
Yeah. Also, yeah. So it's not that we eliminate the sketches. We just there's texture. We can also draw textures, but through this limitation of line drawing.
Now, let me ask another way. What's wrong with the fact that you have a horse and your sketch produces a totally different horse, but still a horse? Why is that bad?
Because in our case, our goal was to perform abstractions that depicts the essence of the object, and the way we define it in this case is that we want it to be recognizable in the instance level. So it's different. It's a different task in terms of like.
So you have you can test later whether some classifier or a person correctly matches the sketch.
Yeah, this is also how we
I
measure
see.
this.
I see.
Yeah. So of course there are works that also only generate sketches from text, and you can definitely do that. But here we explore visual abstractions, so it was important for us to find features that depict the input image, not only the textual level. Okay. So I just want us to look at this column over here. So you see the results obtained with only 4 strokes. It's a highly challenging task, even for humans. We saw that at the beginning with the bicycles. And our results depict the input object quite well, both geometrically and both semantically. For example, we can recognize this is a giraffe. And it's pretty non-trivial that we can do that with models. And I find that this is something that I find very fascinating. Also notably, we were the first work that could generate vector sketches that are not limited to any predefined category, because we were not trained on any sketch data directly, so we can draw whatever Clip knows, and Clip knows a lot of concepts. So we show results ranging from uniforms to sculptures and so on. And the work drew a lot of excitement from the community, so we received the Best Paper Award, the SIGGRAPH, and also it was covered in the news and blogs and so on. And what was nice is that, yes.
So maybe I'm curious. You said you can go to anything clip knows, but if you go to things outside clip, I mean.
Yeah, so we also show some of the clip has some known problems, like these fine-grained differences and some things.
Well, but objects that were not in clip, like the clip language doesn't include. So
a very interesting example of that would be the MNIST digits. So and something known, like we didn't invent this, but clip struggled with recognize these. So what's magical about this work is that it's a combination of what you see and what you know. If you don't know anything, the results will be very different. So we try to find examples that clip doesn't know. So for example, it's very interesting to see that if you insert these MNIST numbers, the result is pretty weird. Like it's only based on the geometry, and you see that it doesn't understand it is drawing the number 3 now. So, but compared to all previous works in this domain, they were limited to, let's say, 100 categories. And this is much more similar to how we, based on our prior knowledge, can draw diverse concepts. And it's not that we are trained, like, you cannot, when you draw a cat, it's not because you have seen like millions of cat images, it's because you know what's important. So this is like the point. Yes?
Sorry.
No, go ahead.
It strikes me that these drawings are very curvy. They seem overly curvy.
Overly, okay.
Are you using a fixed number of control points for each curve?
Yes. Oh.
So you might, I feel like you should be using it would be less curvy if you allowed some straight lines.
Yeah, so you can basically, each cubic bedecker can also represent straight lines.
They
so
can
it
represent
depends.
straight lines, but instead of bounding the number of curves, you might bound the number of control points.
Right. So basically, you can use any primitive that you want that our differentiable is not our, like the differentiable raster as we use supports. And what else I want but learning the curvature, like the number of control points, we cannot backpropagate gradients to that because it's discrete. So it's something that is still limited. Like also, it's challenging to even learn like how many things that are discrete, like how many lines to use or how many control points. And this is still an open question because it's very interesting. Like, of course, we would like to, for example, learn, a less curvy appearance or using less strokes, but we don't have like the differentiable tools to do that yet.
So do you need to select different layers of clip for different level of abstraction, or?
Okay, good question. In this work, we chose specific layers for all the results, but in a follow-up work that I won't talk about, but it's very interesting, you can check it out, clip a scene, we used different layers for different levels of abstraction, indeed. Showing that, I don't know, when you need to draw with less and less strokes, maybe you need to use more what you know, and then we can change, we can actually control this. Okay, so I just wanted to say that this work influenced the diverse follow-up works, and people really used our work, which was quite exciting because sketch abstraction was not the most trendy task, but it drew a lot of excitement from the community. Also, people printed, because everything is vectoric, we can actually print it with vectors and also print it at any resolution. So people also printed the Kipasso generated sketches. And research-wise, it also inspired diverse follow-up works, including sketch abstraction, which now some people also try to advance, abstraction in 3D. Also, people generated data sets with our method to tackle diverse tasks ranging from 3D asset generation to biometric recognition. And I really like this because I think sketches are so useful almost everywhere and we don't even think about it. So I was pretty surprised to also see the application of that beyond what I could imagine. And also the technical components that we proposed, like the geometric loss and also the ascendancy initialization that actually I haven't discussed, are widely used until today in vectographic, in diverse applications from vectographic generation to robotics and also in fabrication. But I see this as the beginning of this field. I think there are many interesting questions that remain. For example, how do you even evaluate machine abstraction? How do you learn the minimal amount of information you need to represent a concept? This is very challenging. And what about more complicated signals? So we only drew images of single objects, but what about scenes? Or what about something even more complicated than that? And what about exploring abstraction beyond sketches? So this is a whole field that I think is very interesting. And I continued exploring that in my work, but we'll go to the next topic. Okay, so ClipAsso kind of sparked my interest in sketches in general, and more recently, I'm very interested in sketches as being a tool to develop ideas and think. So we all used a whiteboard all the time because it helps us to organize our thoughts and also to communicate our thoughts with others. And recently, I have this goal where I want to teach machines to what they call speak the language of sketches. And I envision that in the future, in the same way that today we can chat with ChatGPT in English, and this opened a lot of possibilities that we couldn't also imagine. I think that once we can also speak with machines with the language of sketches that is used in many, many disciplines, this will be awesome. So this is what I'm working on recently, and I want to briefly show 2 works in this direction. Before we move on to the next work, I will dive deep into. Okay, so a lot of things are missing, but recently I've been focusing on these 2 qualities, sequentiality and meaningful parts. So let's just watch it again, sorry. Okay, so here we can see the process of sketch generation made by ClipAsso. All the strokes are optimized together. But this is very different from how humans draw. So humans draw stroke by stroke. The process is really important for reasoning. And also, we draw with meaningful parts naturally. So it would be highly unnatural to use the same stroke to represent different semantic components, like both the eyes and the head. Yes?
Isn't that what caricatures? I mean, caricature sketches that seem to be common, right? To have this long sketches.
Right, yeah. But I talk more about the non-professional, yeah, like the basic, because artists can do that because they are trained a lot on sketches. So they do that from a place of expertise. Naturally, you understand what I mean?
Yeah, but isn't that... continue on.
I want to teach machines to sketch first in the level of competition, I would say, like what this process even represents. Okay, of course I also want machines that can draw like artists, but this should come from a place that they already know to draw like regular humans. If that helps. But it's a good point. Yeah, artists definitely do that, but most people don't. Okay, so recently I want to solve this sequentiality and meaningful parts. And again, with the lack of data, we will need to use some priors of other models. And in ClipAsso, we use Clip. Clip works on a static image, but now we have more advanced priors. So recently, I explored 2 different priors for this task. And I want to show this briefly. So language models are very smart. They have very strong reasoning. They have very strong reasoning across diverse tasks. And they can also describe textually meaningful body parts of concepts, and even their order of importance, which, if you remember in the example of the bicycles, we used a lot of reasoning, right, to understand what's important and what are the different parts. And language models, maybe they cannot draw directly, but they can write code that, for example, they can graph, and this can be rendered into something visual. So maybe inside them, they can also draw. On the other hand, we also recently saw that video models became really strong. So this is an example of a video generated by an open source model, it's called One. And so video models also may have strong reasoning. So you see, to generate something like that, you need to know a lot about different objects, how they behave, and so on. And of course, they have a strong temporal prior. So maybe something like that is also, this prior also hidden inside them. Now let's see what happens if we try to use this prior directly. So language models, multimodal language models has some known problems. So this is a simple example to exemplify this. We asked the model how to connect, how to fill this drawing to form a house. So for a language model, it's a very easy task to solve textually. They know they should connect point 1 and 5. But then if you actually ask the model to produce code that does that, existing models really struggle, it's a known problem, with this fine-grained spatial reasoning. They struggle to find the exact pixels. So this is pretty interesting. So maybe this prior is hidden inside them, but not as easy. On the other hand, video models, this is a Sora this time. So if we prompt them really hard, they can generate something that looks like a sketch process. This is a good signal because it means also maybe they have some prior that is related. But of course, this is very different from what we want. So we show in 2 recent works. This was published. This is still it was not published. That we can distill the prior of these 2 models to achieve sequential sketching. So in Sketch Agent, what we do is that we constrain the model to provide us with parsable sketching commands that we can later parse to fit cubic Bezier curves too. And if you see, we use this numbered grid, which help us to overcome, by design, this fine-grained spatial reasoning limitation. And for the video models, what we do is also very interesting. So we show that we can actually fine-tune a video model in a few shots on a very, very small set of, it's human drawn, but I drew it, human drawn sketches. We can actually distill the models prior to produce videos that look like sketching processes. And in both cases, we also design some additional regularizations to make sure that it's the representations and the appearance that we want. But what's very interesting to explore is that these two priors produce sketches that are inherently very, very different from each other. And I think this shows very nicely the differences between language models and models like video or images that are more image-centric. So let's look at their difference. Okay, these are the results that were created with Sketch Agent. You can see the process feels like much more human-like than what we saw in
Which one is
Clipasso.
Sketch Agent? Sorry, I got.
It's the language model, sorry, yeah. Sketch Agent, these are the results with the language model prior. Okay, so very nice. And so when we use the language model prior, we have by design these meaningful parts. So we force the model to actually annotate each stroke that it provides us. So you can see that all the sketches has this by design very meaningful semantic parts, which is what we wanted. And language models also have strong reasoning, so we show that they can actually draw diverse concepts ranging from animals to experiments in physics and computer science and so on. Okay, but maybe you notice that the appearance is, the appearance is quite simple because that we draw these semantic parts one by one. So, and this is very, let's see the results by video prior. Okay, so you see that the appearance is very different, okay? But each one has advantages and disadvantages. So while here we can get better quality, and we can also more easily control the quality by these few shot sets that we're using. What we saw, I don't know if you noticed, you need to, it's not necessarily always following a valid sketch behavior. So we might see that two strokes can be drawn at the same time because this is in pixel space, it's not parametric, so we don't have direct access to the parametric representation, and we cannot really enforce the rules of sketching. So while the appearance is really good, we also saw some problems in the reasoning. So let's see a bit of more examples of the same concepts. So the process is nice, the appearance is good, but you can see that in terms of the reasoning, maybe the video model does not know all the concepts like language models. So we do see these problems where we try to draw, for example, some famous experiments and so on. We get something that is in the right appearance. It looks like it, but it's not really, we cannot really validate that it functions properly. So there is a gap between these two approaches.
Sorry, what are you referring to here? I'm trying to understand what you're saying now.
So the pendulum motion, for example, I find this sketch to be much better because it actually depicts what this experiment does. And this is not really. Yes?
You say, I missed it maybe, but why does it matter if it's not sketching in the same order as a human? You know, if it draws two lines at once instead of one?
Yes. So maybe I will go here, sorry. Okay. You remember this?
Yeah.
So I want us in the future to interact with models through the language of sketching. So imagine that you talk with ChatGPT. It's a conversation. You say something, the model reacts. So it's not that like you can, the model cannot answer to something you asked in the future, right? So it needs to align in some way with what makes sense to you. So it's the same here. Like if you brainstorm with someone, you want it to react in a sequential way to the things that you draw on the screen. So it's not just one-shot creation, it needs to follow the order. So of course it doesn't have to follow exactly the order, but to some extent we want it.
Now you're talking about understanding sketches, not producing sketches.
So to produce sketches, you also need to understand them. To produce sketches sequentially in a way that is meaningful. So for example, here human and robot are drawing the Clipasso algorithm. So if they are drawing together, the robot needs to understand what the intentions of the human and vice versa.
No, I understand. But if the robot now says that predicts that the human will draw 4 things in some order, then the robot wants to help the human. The robot can just simultaneously draw all of those 4 things at once. There's no problem with that.
Yeah, but depending on the goal. So here we don't want the model to help me to draw more nicely. I want the model to meaningfully react to my process in a way that will help me to solve a problem or come up with a new idea, like we solve an algorithm together on the whiteboard. So here sequentiality is key because it's a sequential process. It's like a visual dialogue. Okay? Okay, and then I also wanted to show you. Okay, so thanks to the meaningful parts and sequentiality, so we also implemented this nice interface where users can draw stroke by stroke with our agent. So it was really fun for our users. It's another example. Okay. It's a bunny.
What was the input? Sorry, what was the input?
The input is the word the bunny.
Okay.
And then the model draw and the user draw together. Okay, so this is the beginning of like this collaborative drawing. But still, it's the very beginning. So we're still far from this goal where we can actually draw very complicated concepts together with computers. Any questions? Oh. Good. Okay. So we talked about abstractions and sketches. I want to quickly show you another topic before we move on to. I will dive deep into another paper after that. Okay. So we said that we have distinct challenges. We talked about abstractions and sketches, but the visuals we use in visual communication, they should not only be visually pleasing, they should also function properly. And function properly depends on the goal and what you're using. But in general, today, while we can generate very beautiful images, we cannot really validate that they function properly. What does it mean? So for example, this Turing machine, okay, it can be represented as a pixel image, but this will be weird, right? Because it has meaning beyond its appearance. So we might want to represent it with something else. And the same goes with many representations that we use in graphic design, that they are not only their appearance, they also have some meaning and they need to function properly. So for example, if we want to generate something, an animation, if we want to use it, for example, in web design, it needs to be suitable for that. Or for example, usually we want to have layers and layouts to have our output be editable. So we need to work with the correct representations. So I want to show you 2 works along these lines that I'm also very interested in.
Just so when you say function here, you still mean function in the context of graphics, like not that the bird can fly, only that I can animate it to
Yes,
make
it's
it
more
appear
about
like
the
it fly.
representations that you're using.
Okay.
So sometimes this is like goes beyond pixel. Like sometimes maybe a lot of things are images, they are visual, they can be represented with pixels, but a lot of times it would not make sense.
I understand, but like the Turing machine, you don't mean that the Turing machine actually does what we want. You just mean that I can like edit it
exactly. Yes.
visually, just like function in a visual, still just in a visual sense.
Yeah, it means that to represent it, and if you want to verify it is useful, it will be weird to represent it just with pixels. So it's just an analogy in a sense, because it has structures and rules. Okay.
You have to be careful walking into a theory department and saying that you're
No, but it's not a.
No, but
It's just if you want to draw a Turing machine, you need to know how it works. Otherwise, it's not like generate images.
So this is what I was confused by. Like when you say function correctly, you mean function that what this represents functions correctly, or just that I can, move things around and the arrows will point.
It's both because it's not. Yeah, because this is for example a directed graph. If you had like 2 arrows here, this will be like invalid. But in a pixel space, it won't be very different. Understand what I mean? Small changes in
No, I understand.
yeah, it's weird to represent any graph.
No, so then
Any
you just,
graph has rules. It's weird to represent a graph only with pixels because it has like another dimensionality. It has another.
No, that I understand. But they're saying the function is in the visual, just in the visual sense function, not like
It
not in the
has
real world.
meaning.
That's different.
You can use it as to be able to use something as a graph, only representing it with pixels will be like not the most optimal representation. Anyway, but this is just an example because my work is not about generating images of Turing machines. It's
No,
about
but take the bird. Like the point is, the bird doesn't have to be flying in a way that's physically realistic. You just need to be able to
You just want
animate
to generate something that can later be animated in a way
Yes.
that makes sense.
Exactly.
Okay, so all of these representations go beyond pixels, but today models are mostly focused on generating pixel images because they are widely available online and so on. And in another line of work that I worked on after Kipasso, so if you remember, in Kipasso we optimized parametric representations with priors from pixel models. So for parametric, so the representation I work on is mostly vector graphics. And I want to show you two very nice applications that were enabled with using priors of pixel models to produce vector graphics visuals. So the first one is word as image. Here we deform the shapes of letters to convey the meaning of the word. And we'll see another example. So these are very nice. They can be used, for example, in novel design or in books. And also, I think just conceptually, it's a very challenging problem, similar to what I showed you with the bicycle. So you also need to have some visual understanding of the shape of the letter. And you need also to make decisions on how to fit the visual meaning of the concept such that it fits naturally into our letter. Okay, so you need to make this also visual and also semantic connections to solve this task. So what's nice about this work is that first, we use this similar approach where we solve this by deforming the shape, by using the pixel prior, and we also design some regularizations on the shape itself to make sure that the result fits naturally into the font. So this font, for example, is thick, and this font is thin. So it's not just deforming the shape without any regularization. We have to make sure it looks good and also that it's still legible. Okay, but these are more technical details. What's in the context of what we said, what's I like about this work? So fonts and letters are generally represented with vector graphics. It doesn't make sense to represent it with pixels because we need to print them. All the PDF, for example, is using parametric representation. So if you implement such an idea with pixel models, you cannot actually use it as a valid text. So you cannot use it in PDF. And also, when we use vector graphics, the output is very editable. So if a designer wants to use that, they can very easily move things around, choose a subset of the letters that they like, scale, and so on. So using vector graphics here is the correct choice. Another example that I want to show that we did is animating static sketches based on text prompts. So users can provide their parametric sketches, and then with the prior of video diffusion models, we optimize the parametric representation, but this time across frames. In that way, again, with additional regularizations, we can animate the sketch to follow the text prompt. Let's see another example.
So what the user provides here is a vector sketch or just a
vector sketch?
A vector sketch. So user
the prompt, and then we animate it based on the prompt. And everything is in parametric space, so it's also the right representation for the vector graphic animation, and it's editable across frames. So, okay, so I think these are examples of the power of pixel models as priors for parametric generation.
What do you mean by editable across frames?
Because it's parametric, so you get the parametric representation of the entire video. So if you want, for example, if I didn't like how the head look at some point, you can very easily change it because it's in vector space.
So you're editing the appearance, not the motion. Or in a way,
Yeah,
you're
you can-
editing the motion. You can edit
Yeah, you
frame
can
by
also
frame.
you can edit
and so you
anything.
No,
Yeah.
but you can edit.
So if you edit,
But you don't have.
You edit the motion. If you move it in one frame, it's gonna change it in.
Sure,
other
but you
frames,
don't
so-
have a knob on the motion quality that is
Oh,
the
Yeah, if you are a motion animator, you can edit the motion, but it's hard.
But the motion, whatever you get out of the video model is what you get. There's no way for you to unless you do it by hand. Pretty much.
Yes, but that's always the trade-off when we use these models. that I believe in, that we want them to produce us with something reasonable and editable, so I will also have a say on the output. And pixels are usually not editable. Yeah. Yeah.
Oh, sorry, go ahead.
If you were to edit an individual frame, what happens to the frames, the other frames?
So the editing can be performed only after the result is obtained, but you can edit it, and basically it's an instant optimization. So actually you can edit it and just feed it to the optimization if you want to change something.
And then it updates the adjacent frame.
Yeah, you can do that.
Okay.
Yeah, it's not that like the output is fixed. You can always change it.
Is it the same number of strokes for every frame?
Yeah, so it's by design. Like what we do is that we copy all, like you provide the initial sketch, we just copy it, and then we learn the deformations also across the frames. Okay, now I will skip because I want to tell about another work, so I will try to say okay. Impact, let's skip. Okay. Sorry for the later. Okay. So the last part I wanted to talk about is a different perspective of this visual exploration. If you recall, we said that one of the challenges is that these images that we use are part of some process. So we saw that sketches are also part of the process. And while today, when we think about text-to-image generative models, we mostly think about them as being used for this, what I call the final stage of execution of idea. We already have some very well-defined vision. We can find a very specific prompt, and we generate an image. But I think that these models also have potential to serve us in much earlier stages of developing of idea. So we saw that in the sketching, this is one potential, but I also think that image generation has big potential in helping us when we want to find new ideas and serving as inspiration and helping us to explore what we do. So the motivation is that we all know that thinking about new ideas is not trivial. As researchers, we do that all the time. No, it's easy for you. For example, how do you think about your next project, or how do you solve some algorithm? It's hard. What we do, for example, we read a lot of papers, we go to seminars, we talk with our colleagues. All of these can be thought of as acts of seeking inspiration. Maybe I will go to a talk, I will hear something, it will give me an idea. Or maybe I will read a paper, I can take one component. And in addition, we explore ideas. I have an idea, I can code it or write it and see if it works. And this is exploration. I just try out things. And this is basically core to the creative process. And in design, it's very similar, actually. So designers and artists also seek inspiration in others' work or in nature. So a lot of the things we see are actually inspired by something else. For example, the lotus temple is inspired by the lotus flower. But this, so when we take an inspiration for something, we don't simply copy it exactly, right? So the lotus temple is just took the structure of the lotus flower, but it's not a complete replica. So this ability to take a visual concept and think about its different components is important for creating something new. So imagine that I have some object at home that inspires me. And now I want to explore some ideas. So maybe I want to draw something based on one element of this object. Or maybe I want to explore a design of a chair based only on the texture. Or maybe I want to design a new coaster with my cat. So I want to be able to decompose it into its visual elements, take only parts of it, and also explore some ideas freely. So in our work, Inspiration Tree, this is what we do. So given some input image of some object of inspiration, we decompose it into this structure of a hierarchical tree, where each node in the tree represents a visual sub-aspect of the concept, okay? And this tree can already give us inspiration, maybe to create something new, because now I see some aspects, maybe they are surprising. And also we can use it to explore ideas. So I can take one node from the tree and generate some design that is inspired by it. For example, like the drawing of a cat that is inspired only by the texture. And I can also explore variations of my object by excluding nodes from the tree and reconstruct my original object, okay? So this can help us to quickly explore and think about ideas. Okay, I will skip. So I want to tell you details of how we implement it, but I will skip. So basically, okay, so we use the priors of diffusion models. These are generative models that can generate new images based on the, okay, I will just explain it. We have to finish at 1 exactly, or yes? Okay, I'll do my best. So anyway, how diffusion?
12. Not 1. 12.
No, it's okay. So, anyway, very quickly, in a nutshell, diffusion models, given a text prompt, we encode it into a set of vectors. These vectors sit in what we call a textual latent space, okay? We can think of, like each word is encoded into an individual vector. And then we have a diffusion model that can generate new images by gradually cleaning a noise signal. In our case, the signal is an image. Great. So in a work by Yael et al., they show that you can actually inject personal concepts, like an image of some object from your home that the model probably has never seen, to this textual latent space, such that if you feed now the sentence, condition the generation on this embedding, you will get images of your personal object, okay, without changing the weights of the network at all. This is amazing. So this idea inspired us to think that if the concept can be found in this textual latent space, maybe the different aspects of the concept can also be found there. And we show that indeed that's possible. So in a nutshell, how do we do that? So our goal is to find these two vectors that together compose our parent node, so which is our image. And what we do is, it's an optimization process that is performed, in a sense, implicitly. So we want to find this decomposition without forcing its nature. So we don't want to tell, like, this should be a bear and this should be something else. We want it to happen naturally. So we initialize these embeddings with the embeddings of some general term, the word object. So at the beginning, if we feed this to the model, we'll get some image of some objects. And then it's an optimization process. So what we actually want is that if we feed this sentence, if we condition the generation on this sentence, we want to actually get images of our object and not the word object. And then this is our objective. So we optimize this goal. And what we find interestingly is that when these two vectors are placed in a sentence one next to the other without any additional constraints, they naturally tend to diverge and depict two aspects of the object. Okay, so this happens naturally without additional constraints. So, okay, this is magical. I did it first, but you should be excited. But anyway, this is pretty interesting. We do find that in some cases, these two vectors tend to diverge. Together, they can compose the input object. But when you generate images for each one individually, the images appear quite random. And I'll skip this, but we can actually filter this automatically with clip. Okay. Then we can build this tree recursively. So now we have V1 and V2. Now I want to decompose V2 into its two different sub-aspects. And I just repeat the same process. So I initialize these two embeddings with the word object. And now I have access to V2, so I can generate images as V2 and use it in my optimization goal where I want V3 and V4 together to generate images of V2. This. Okay, I just want to show you this. So this is the tree constructed for this sculpture of the cat. Okay, so in the first two levels, maybe the decomposition could be quite expected. Okay, so it's this cat-like sculpture and these colorful stripes. But in the next levels, which I like, we start to see something interesting. For example, this that looks like some plant or some worm, I don't know. This might resemble the tail of the cat. So this gave us some aspect that I wouldn't think of, but the model kind of surprised me. And this is the whole goal of doing this decomposition implicitly, so that maybe the model could find aspects that we cannot think of ourselves, and this will inspire us to create something new, something creative. And so we can explore concepts within the cat. And what's very nice about this method is that you can also actually combine aspects of two different concepts. So here we took this cat chair from the cat sculpture, and here the stone surface of this Buddha. And we can generate these hybrid sculptures that also may inspire us to create something new. Okay, great. So we did it almost. We covered almost the entire map, and we do have like 2 minutes to tell you about our future thoughts. So what's next? So the spectrum is very, very big, and there are a lot of exciting future projects that I want to work on. So recently, as I told you, I'm very focused about the goal of teaching models to speak the language of sketches. And while I'm working on sequentiality and meaningful parts, I'm also very interested in this more enhanced spatial reasoning in models. So not only using the prior of existing models, maybe training something that will have these objectives or have this understanding more rooted in the model. But for that, we need the data. So recently at MIT, actually got approved to collect for the first time data of sketches and reasoning together from math classes. So today, thanks to COVID in a sense, a lot of classes are online. And this means that teachers, like a lot of sketch data is just not being used. So what we do is that we can collect all of the sketch data, all of the parametric sketches. So it will now contain both the parametric and the visual, which is like these two things that need to click at some point, and all the reasoning behind it, which is everything that people say. And in the future, when this data will be big, we might be able to train a model with a more inherent such understanding. Okay. And in addition, I'm very interested in, okay, so we use the tool of a pencil. It's a building block, but basically humans can learn to use it for different languages in a sense. So for example, I've learned at some point the language of computer vision, but I didn't know that before, right? Or you can learn to draw sketches of fashion. So we can use this tool in a very versatile way. And I want to develop machines that can also do that, use this tool in a versatile way. This is very hard. Okay. In addition, I'm very interested in visual communication in challenging scenarios. And I think scientific figures is a very good example. Scientific figures are very diverse and they are very complex. For example, if we look at this figure from biology, so many elements, maybe it explains something very complex, and it's hard for humans to create such figures that are good and really communicate something. Imagine how nice it would be if I could explain like anything with a visual that is super clear and super clean. And this is hard, but in the future, I imagine that we could develop models that can actually do that. And I think this will change the way we exchange information with each other. Okay. And lastly, this is maybe a bit of more exploratory. So let's assume we have models that can draw or can communicate with visual elements. What can we do with them? So I imagine that maybe we can let them draw together or alone to complete some visual tasks. And this was shown successful in other domains, like games. So imagine that models that can draw, similar to how we solve problems together on a whiteboard, maybe could find very interesting ways to solve visual problems, ranging from math to design. Maybe they could invent designs that we haven't thought of, or invent some new visual conventions, and this will be very interesting. Okay, that's it. Thank you.
Okay, I'll let you guys have one question, if there is one burning question.
Maybe, what happened in the last part?
No question. Okay, so wait, one question, please. Avi.
So, what do you think is language necessary for visual thought?
What?
Is language a necessity for visual reasoning and visual thought, like abstraction of?
Okay, I don't know if language is the word, but maybe symbolic reasoning is, I think it's definitely, like, it's my opinion. My hypothesis is that it is necessary, but it's not necessarily must come from language. It can come from something else.
Okay, so in that case, thank you very much, Yael.
Yes.